Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at the pigeonhole principle, which says if n plus 1 pigeons are to be placed in n holes, then at least one hole contains at least 2 pigeons. So to illustrate this, here I have 6 pigeonholes, and over here these represent 7 pigeons. So of course, if I start by placing a pigeon in each hole, eventually I'm going to run out of holes. I'm going to need to put this such that at least one hole has at least 2 pigeons. So this is kind of a worst case scenario. Of course, I could have a situation where multiple holes have 2 pigeons. But like the worst case here is that I will have at least one hole that has 2 pigeons. Now this probably sounds extremely basic. You might be thinking, yeah, that's obvious. How can that possibly help us? Well, we can use it in maths to prove seemingly unrelated results. So let's look at this question. If I place 5 points inside an equilateral triangle of side length 2 centimeters, we're going to prove that at least 2 points must be within 1 unit of each other. So the way that we're going to do that is we're going to divide this here into 4 smaller triangles. So what we're going to do is join the midpoints of each side. So if I join up these midpoints, I now have 4 triangles, and these sides here will be 1 because the original side length of the equilateral triangle was 2. Now, because this angle has to be 60 degrees, as happens in any equilateral triangle, each of these 4 triangles is equilateral. See, if you have an isosceles triangle in which one angle is 60 degrees, it must be equilateral. So all of these sides will be 1 as well. So where does the pigeonhole principle come into this? Well, we have 5 points to place inside 4 triangles. So the pigeonhole principle tells us that if we want to place this 5th point, it's going to have to be in the same triangle as at least one of the others. So maybe I could place it there. So we must have a situation where these 2 points, also these 2 points and these 2 points, they will all be within 1 centimeter of each other. It's impossible to place 2 points inside an equilateral triangle of side length 1 that are more than 1 centimeter apart. If they were more than 1 centimeter apart, they would be in different triangles. So again, this is a worst case scenario. We will have at least 2 points being 1 centimeter from each other. Of course, we could have more than 2, but we're guaranteed, we're absolutely certain that we will have 2 points that are within 1 centimeter of each other. Let's look at another example. So my sock drawer has 12 black, 8 brown, 4 grey socks. I'm going to pick them randomly from the drawer. How many must I pick to be guaranteed that I have at least 3 brown socks? So over here, use this idea of worst case scenario. What's the worst case scenario if brown socks are what we want? Well, if I pick 16 socks, they could be all black or grey. It's unlikely that they'd all be black or grey, but it is possible. Remember, the question asked how many we must pick, so we're guaranteed to have 3 brown socks. So 16 isn't the answer. I would need to pick more. Now, if I pick 17, the pigeonhole principle guarantees at least 1 is brown. Here it's like I have 17 pigeons and there's only 12 plus 4, 16 black or grey holes. So worst case scenario, if brown socks are what I want, is if I pick 17 that I get 1 brown sock. And similarly, if I pick 18, I must have at least 2 brown socks, and therefore if I pick 19, I must have at least 3 brown socks. So 19 is the answer to this problem. The pigeonhole principle guarantees if I pick 19 socks, at least 3 must be brown. All right, let's look at a harder problem now. So here I'm looking at the integers between and including 1 and 10, and I'm going to show if I pick 6 such numbers, then at least 2 of them must have a difference of 5. That is, of the numbers I pick, there must be at least 2 of them such that if I subtract the smaller from the larger one, I get 5. So how we're going to prove this is we're going to divide into subsets. So the numbers I can pick 1 and 6. I can pick 2 or 7. So each of these is a set. That's why I'm using the squiggly brackets. And the 2 numbers in each set differ by 5. So notice that if I write out these 5 sets here, and I pick out 6 numbers, the pigeonhole principle guarantees that I must pick at least 2 elements from one of these sets. So here, each of these sets is like a pigeonhole, and the numbers I pick are the pigeons. I'm picking 6 pigeons and putting them into 5 holes. So these sets here and this sentence here are all the proof you need. Proofs involving the pigeonhole principle are often very short and rely on common sense. But just to reiterate, the worst case scenario is if I pick 5 integers, I could pick 1 from each of these sets. But then if I pick a 6th integer, it must come from one of the sets from which I've already picked. So I'm either going to pick those 2 numbers, or those 2, or those 2, or those 2, or those 2. In any of those cases, I have 2 numbers that differ by 5. All right, let's now take a look at the generalized pigeonhole principle. So the generalized pigeonhole principle makes extensive use of this ceiling function here. So let's quickly go through it. So if you input into this function a number that's not an integer, like 2.3, you always go up to the next integer. It's not the same as rounding to the nearest integer. We always round it up. So the ceiling of 7.9 would give us 8. And if you take the ceiling of an integer, it just stays as it is. So the generalized pigeonhole principle says that if n pigeons are placed into k holes, then at least one hole contains at least this many pigeons. So let's look at an example. So suppose that there are 250 people in your grade. We're looking at their birth months. So the generalized pigeonhole principle tells us that at least one month will have at least this many people who have a birthday in that month. So if I put 250 over 12 in my calculator, I get 20.83 recurring. So the ceiling function says we round that up to 21. So if there's 250 people in your grade, there is at least one month in which at least 23 people were born. So again, this is kind of a worst case scenario. There might be multiple months in which 21 people were born, but we can say for certain, without knowing anything about the distribution of birthdays, we can be certain there is at least one month in which at least 20 people have a birthday. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.